Okay, so this is what we were discussing, the flatness of the maximally flat filter response. So that means, so this maximally flat response is also called as the binomial response, so which is or Butterworth response. That we have, so that if you see the response of this one in the past band, it is a flat kind of thing. So you can see here in the past band, it is a completely flatness we are going to achieve. So that is a possible thing. The flatness is it is in the past band. Maximum we are going to get the flatness. So that's why it is called as, also it is called as an optimum filter. Okay. So now if you see the low pass filter, whatever we designed here, so that is the response whatever we have here. So that filter response, so we can express that in terms of the insertion loss or power loss ratio, that is PLR, which is equal to 1 plus k square into omega by omega c whole power 2n. Now you can see here this omega c is the cutoff frequency. So you can see this is a cutoff frequency where we have that cutoff frequency will be having the magnitude value of this much 1 plus k square, where omega equal to becomes omega c, because this is your omega axis. Okay, so when this omega which is equal become equal to omega c, so you will going to get the magnitude value of 1 plus k square. Okay, so now n is the order of the filter, so that we know already order of the filter. Okay, so now omega c cutoff frequency. Okay, omega c is the cutoff frequency. Now the pass band is, so generally we know it is exists from omega to omega, that is 0 to omega c. So this what will going to exist the pass band. So now that, so whenever we have the at exactly pass band edge omega c, so this magnitude whatever we have 1 plus k square, so generally that we will going to take it as minus 3 dB down. Okay, so whatever we have maximum value 0 dB, so this 1 plus k square, whatever the value which will going to come, so that it will going to equate it to minus 3 dB. Then we can able to find out what is the value of k. Okay, so now that's what, if we choose this 1 plus k square as minus 3 dB, so then we can have, so this k value, so which will be equal to, commonly we can choose it as 1 also, but whatever the k value, that if you choose the k value so 1, so you can possibly get, so the thing which is minus 3 dB. And if omega is greater than omega c in the stop band, okay, so if you go to the stop band here, if omega is far greater than omega c, then what your power loss ratio will going to get, so it is nothing but approximately for this case, it is k square into omega by omega c whole power 2. Okay, so this is for the stop band, whatever which is having omega is far greater than omega c. So this equation will going to be approximately k square into omega by omega c. So that is whole power 2n. So now this which shows that the insertion loss whatever we are getting, it increases at the rate of 2n. So this is actually the insertion loss factor, which is actually based on the filter order. So that insertion loss, so we can see here whenever it is at the 0 omega frequency, omega equal to 0, it is having maximum. And whenever we are going increasing the frequency, the insertion loss is going to be decreased. Okay, so that is insertion loss will going to increase. Okay, insertion loss is 0 here, and it is going increases with respect to the filter order. So that actually so depend on the 20 n dB per decade. Okay, so then if you know what is the value of n, based on that this slope will going to increase. So that is the slope will going to change. Okay, so now if you take that, so filter response for n equal to 1, n equal to 2, like that. Now if we have, so like this, now if you take the first order for n equal to 1, it may be 20 dB per decade. Okay, so now if I take some second order filter, so you may get some sharpness here. So that is roll off will be 40 dB per decade. Okay, so similarly, so still if you have something like 60 dB per decade like that. So now this flatness it is going to be so based on the order of the filter, and also the loss will going to increase, and suddenly that sharpness, the role of sharpness it will going to. Okay. So now this, like whatever binomial response, we can use that multi-section quarter wave matching transformers. Okay. So we can have the based on the number of the order, the filter order which is having n. So we'll be having two n minus one derivatives. Can take that two n minus one derivatives. So that kind of multi-section quarter wave transformer we can able to get that. So then what we can do, so we can have that, so the whatever we have the stop band, that is k square into omega by omega c whole power 2n. So this is what PLR for omega far greater than omega c. Okay, that stop band whatever we have. So then, so this almost it will going to be so approaching to zero. So whenever we have taken 2n minus 1 derivative at omega equal to 0, so generally it will going to be so the maximum at this omega equal to 0, and omega it is far greater, then it will going to approach tend to 0. Okay, so that means attenuation increases monotonically with the frequency. Just whatever attenuation, insertion loss, whatever we are getting here. So if you take this level, okay, so this is a 0 dB level. So this attenuation which will go on increasing. That means in insertion loss it will go on increasing. So when you go on the frequency, so if you go on increasing the frequency, that is far greater than omega c, it will almost tend to 0. Okay, so that is what. So that we can achieve, we can take 2n minus 1 that much multi-section quarter wave transformer in our filter design. Okay, so now you can see equal ripple also. So that we have already seen equal ripple filter. So that is nothing but a kind of Chebyshev response. So we already seen what is Chebyshev response, and so how the ripples it will going to happen. So we'll be having the one plus k square, that is 3 dB level, and we have the ripples in this particular so band. So from 0 to 3 dB down. Okay, so minus 3 dB down. So within that we have some equal ripple. Okay, so and then we'll going to get some filter response like this, and also we have the in the stop band also. Okay, so in the stop band also we're going to have some so something like ripples like this. So then again that stop band also we need to take, and the cutoff frequency whatever we have 0 dB, so that it will going to give so omega c, and within this we're going to get the pass band. Now this kind of response which will be called as equal ripple, or we can have emission. So that we already you might have discussed in the signal processing and all. Okay, so here the insertion loss, so it is so for the nth order low pass filter, the insertion loss or power loss ratio can be defined in terms of the polynomials, that is 1 plus square, okay, into Tn square omega by omega c. So this Tn it is nothing but a polynomial. Okay, so that means the sharper cutoff will result. So whatever this the sharper cutoff will result. So although the passband response will have the ripples here, so from here to here, although so this having a ripples, so we will have the the 3 dB down, that is exactly same as the flat that maximally flat filter, which will be having 1 plus a square. Okay, so now this Tn of x, whatever we have the polynomial, okay, Tn of omega with respect to frequency, or Tn of x, we can take it as with respect to some polynomial of it is a function of x. So that Tn of x, which actually oscillates between that plus 1 and so this the absolute value if you take plus 1, and it will be 1 plus k square, and this will be oscillate between here, so this values, that is absolute value 1, and we can take this value 1 plus k square. Okay, so that, and this will be if you take Tn of x, this will be oscillate between plus or 1 minus 1 for the magnitude of x square. Okay, so the magnitude of x square if you take, or if you take magnitude of the function, so it will be the oscillation which will happen between plus 1 and minus 1. So the k square value, whatever we have here, that k square value, it will going to determine the pass band ripple. So based on the value of this one, k value, and then the polynomial, whatever we are going to achieve. So based on that, we are going to get the pass band ripple level. So it may be high or it may be low. Okay, based on that values of the polynomial and k value, you will going to get the pass band ripple level. Now, if you take the larger value of x here, okay, so if you take the x value larger, so that Tn of x polynomial. So if you can take the Tn of x polynomial, okay, so that will be so based on the again so the filter order and the term which is x. So for larger x, okay, for the larger value of x, and this is for omega is far greater than. Okay. So now the insertion loss for this case, what it will become? So that TLR, which is equal to approximately k square by 4 into 2 omega by omega c whole power 2n. So now this is for the stop band ripples or stop band case, and which we discussed earlier the equation which is for the pass band. Okay. So now which so whenever we take that condition which is for omega which is far greater than omega c, it is increases again at the rate of again 20 n dB per decade. So even in this case also the rate of the change which will be based on the filter order only. Okay. So but however the insertion loss for this Chebyshev case, so again, so if you take the filter order, so that again it is varying with respect to sorry. So again it will vary. So 2 power 2n and divided by 4. And this one the insertion loss varies. So here, so if we can take the filter the insertion loss variation, attenuation variation. So that insertion loss variation happens in this response. It will be 2 power 2n by 4. Okay. So, and which is greater than the binomial response, whatever we earlier we have said. Okay. So there it will be 20 n dB per decade we are going to get, and for omega greater than omega c, so it will also happen in this case 20 n. But whenever we have the pass band in this case, that insertion loss increases with respect to this value. That is 2 power 2n divided by 4. Okay. So now this is about the equal ripple, and then we have again another the function which is elliptical function, right? So that we have earlier discussed. So the maximally flat and equal ripple or Chebyshev response both have the monotonic that increasing attenuation, monotonically increasing attenuation. So you can see here. So both are actually increasing with respect to this 0 dB level. Monotonically, this the insertion loss which is on increasing. Okay. So in the even so from the 0 dB level and also in the stop band it will go on increasing the attenuation. But in many applications, so we need to so minimize that stop band attenuation. So that is very important the stop band because this it will going to affect the pass band frequencies. This attenuation level if it is high like this, it will going to be affect the pass band frequency. So then it will the interference will happen so that it will not filter the exact frequency which we wanted. Okay, so that's why in many applications we want the minimum stop band attenuation. Okay, so in which better cutoff frequencies need to be obtained. Okay, so that the sharper how much the sharper roll off is. That's why this roll off will always be very much sharper in the practical filter design. So that's why they will use the more number of order filters, that is n, 10th order, 12th order, 15th order, like that. Okay, so now this if you obtain the attenuation in the stop band which is minimum, so that can be obtained using this elliptical filter. So that stop band attenuation if we concentrate, So one type of filters we can design. So in order to achieve that stop band attenuation very so minimal, that kind of filters we can call it as elliptical filter. Okay, so that filter function. So why this will be called it as elliptical filters is that filter function, it will be function in the form of elliptic function. So the filter response, it will be the form of elliptic function. So that's why we'll call it as this one elliptic filter. And we have even so even we can reduce that the ripples whatever there in the Chebyshev response. That ripple, pass band ripple, auto stop band attenuation, ripples in the stop band attenuation, that we can reduce in the elliptical this filter design. Okay, so this is what we have that elliptical. Generally, it is difficult to synthesize because we are concentrating both the pass band as well as stop band. So that's why it is slightly difficult to synthesize. So practically, so that's why most of the applications so they will not use this. But whenever the specific application requires both the minimization in the pass band and as well as stop band, they are going to use this elliptical filters. So now next we'll come to the linear phase filter. So that I've discussed in the earlier class also. What is this linear phase filter? So till now whatever we discussed the filters specify the amplitude response, but we are not concentrated on the phase response. But in some applications the phase response is also very much important. Okay, so if you take the multiplexing filters in the filter multiplexing systems and all, so the derivatives of that, in that it is very important the phase of the filter. So that means we need to operate the filter in the linear phase response. That exactly in the pass band we should have to get the linear phase response. Okay, so that linear phase response what it will give, so it will not distort the signal. So whenever we take the pass band, okay, so in this pass band the phase should be linear. Okay, so it should not be non-linear kind of thing. Okay, so if it is linear, then that linear phase it will avoid the signal distortion. Okay, so linear phase will avoid the signal distortion. Otherwise, if it is non-linear characteristics, the phase, so you are going to get some distortion and you will not get the filter properly. Whatever we need to filter the frequency component, it won't happen properly. Okay, so the sharp cutoff response. So generally, so it is incompatible with a good phase response. So whatever the sharp cutoff which is there here, in those kind of, so if we have the very sharp cutoff, okay, so in that kind of the filter, generally it is incompatible that the magnitude response which is we get the sharp cutoff, it is incompatible with a good phase response. If you calculate the phase response, so that is not compatible. The somehow the magnitude and phase will not be compatible. So the phase response of the filter must be so. In this case, we need to very much clearly synthesize the phase response. Okay, in order to get the good filter characteristics. Okay, so this is about the linear phase characteristic filter. And if you see the response with respect to the phase of the filter with respect to the frequency, so that it will give a omega into 1 plus p into omega by omega c over 2n. So now this is what the phase response with respect to the frequency. Phase of the, so we can see this, we can call it as the phase of the voltage transfer function of the filter. So this is nothing but the phase of, so generally we take it as voltage transfer, okay, of the filter. And so this P is a constant, P is a constant. And so with respect to this, so whenever we have the phase, we also define the another term which is called as group delay. Okay, so that group delay is the function of again to the omega. What is the phi? The derivative of this phase response which will give the group delay. Okay, so this is called the group delay. Okay, So now this group delay, so it is a function of the phase, and if we can derive that, we are going to get A into 1 plus T into 2n plus 1, okay, into omega c whole power 2n. So if you take the derivative of that, we are going to get, so 2n plus 1, so 1 plus T into 2n plus into omega by, that is what you are going to get the group delay value. So now if you see the process of the filter design, so this is what the linear filter, that is linear phase filter, and how the phase response we are going to have with respect to the omega and other of the filter, and this is the expression for group delay. Now if you see the filter process, so these are all the filters which we have commonly physically realizable, that is maximally flat, equal, ripple, and then even elliptical, it is still difficult to realize, and also the linear phase filter. If you go and taking the whatever the practically how the process it will happen, but we are going to take the filter specification. Okay, even we can have the process which is the filter design. So generally we are going to take the filter specification what we want, whether it is a low pass filter design, high pass filter design, what is the cutoff frequency, and how much ripple if it is want, the ripple, stop band, and pass band ripple, everything will going to take the filter specification. Okay, once we take that filter specification, whatever may be the filter design, first we will design low pass prototype. So this is very important step. Whatever may be the design, the final design, first the filter specification once we get, we will going to have the next stage low pass prototype. Now once we get that low pass prototype, so we need to scale the frequency and other parameters. So that's why we'll in the next stage we're going to have scaling and conversion. Okay, we're going to have the scaling and conversion. Finally, we can have the implementation. That implementation part, what we can do, what will be the, so the filter design expected from the low pass type, we can convert that low pass to whatever the filter design we need. Okay, so that is what we'll get going to get the implementation part. Whichever may be the final. So let us take the filter design. I want the band pass filter. So for that band pass filter, first I am going to take the filter specification and I will convert it to low pass prototype, and then I'll do everything scaling, conversion, frequency, and the conversion omega and everything in radians, whatever we need in it and all. Once we done that, we convert. There is a conversion parameters which are there from low pass type to high pass, low pass to band pass, low pass to stop or band stop, like that. That conversion we're going to do in the implementation part, so that we're going to get the final result. Okay. So generally, while doing that, we're going to normalize the filter in terms of the impedance and frequency. So that is very important. So whenever we start the process of filter design, so we first normalize the response or normalize the filter in terms of the impedance and impedance and frequency. So this is very important. Normalize with respect to what? Normalize with respect to generally cutoff frequency. Okay, so that will be the always the key parameter. So the normalization with respect to frequency will be having, so normalization always with respect to cutoff frequency. And impedance, it is always normalization with respect to the characteristic impedance of the filter. Okay. So now this normalization which will simplify our design of the filter for any arbitrary frequency and arbitrary impedance. So you can take that any arbitrary values and you can able to design, because we already normalize with respect to those frequency and impedance. So what may be the value, we don't bother, just we're going to design. So that's how the simplification happens in the. So are then again scaled into whatever the desired frequency and impedance. So after normalization we'll go and design, and then later we can again scale and conversion, we'll do the required frequency, and then we'll finally redesign with respect to lumped element components, whether it is LC filter, RC filter, we can have the distribution. So after conversion from low pass to high pass and all those things, we actually go into the whether it is circuit elements we need to use or lumped elements, or we can use the stub kind of thing, that is distributed elements we need to use for the filter implementation for the higher frequency. Whether we are designing at the lower frequency or whether we are designing at the higher frequency. Based on that, we are going to select the element, whether it is a lump element or whether it is a distributed element. Okay, so this is a filter process. So till now, whatever we discussed, is it clear till now? Any doubt? All of you got it? Okay. Okay, so then we'll stop here. We're going to design the maximally low pass prototype in the next class with equation and everything, how we can able to design the low pass filter. Everything. Okay, we'll stop here. So wait for a minute. I'll take the internet. Is it clear? Any doubt in this till now? Okay, so we'll discuss tomorrow.